If I could have your attention, please, we're going to go ahead and get started. My name is Chris Barkin, and I want to welcome you all to the first William W. Hay Railroad Engineering Seminar for the fall semester here at the University of Illinois at Urbana-Champaign. Before I introduce our speaker, I'd like to take care of a few housekeeping items. The first one is if you have a cell phone, please take it out and do what I'm about to do, which is to turn it off or make it go vibrate so we don't disturb the speaker. So a little bit about our health and safety. If we have a fire alarm, exit from these doors and take the nearest safe stairway to the first floor. And we have a stairway out there by the windows on the east side, and then there's a stairway right out here on the right on the north side. Take those to the first floor, exit the building, and I would ask everybody to assemble on the north side, on the opposite side of the street, near the Hydrosystems lab. And I would ask also if everybody could pay attention to who's next to you. You will use the buddy system and make sure that your buddy gets out safely along with you. I don't think we're going to have any severe weather, so I won't explain how to get to the basement. We'll be passing around an attendance list. If you could please sign this, identify your name and your company. And if you did not receive a direct email announcement about this seminar, but you would like to add your email address legibly to this list, and we'll add you to the list. And if anybody wants continuing education unit credits, just please check the box and we'll take care of that. We're, as usual, joined by a number of people from off campus who are connecting via the internet, and I want to welcome them. We have representatives from Parsons, New York State DOT, Alfred Benesch Company, URS, Parsons Brinkerhoff, HDR, CSX, Michigan Tech, BNSF Railway, MIT, Metra, and University of British Columbia. So welcome all of you on the who are joining us via the internet. And I would also remind those of you who are connecting via the internet, if you'd like to receive continuing education units for your participation, please send Katya an email. Her email address is in the announcement of this seminar. I'll also, I guess it isn't really necessary with our new technology, but if the speaker could periodically just say which slide we're on, just to make sure that people are following along from over the internet. And if there are questions, it would be helpful. If there's questions here from the audience, it would be helpful if you can repeat them so that people on the phone or on the computer can hear you. So at this time, I'd like to introduce our REMA student chapter president, Brendan Corin. He's going to announce our happy hour in honor of our speaker today.
Good afternoon, everyone. This afternoon at 6 o'clock, we're going to be hosting a happy hour at Legends on Green Street in honor of our guest speaker, Rex. So feel free to join us. There'll be free appetizers provided.
Can we start sooner?
Well, yeah, I guess we could send out an email. Okay. We'll make it 5:30. 5:30 is the new time.
Okay. So anyway, I would encourage everybody here to, whether you're a member of the REMA student chapter or not, all are welcome, of course, and you can join in continuing the discussion with our speakers. We'll be there today as well. All right, well, the William W. Hay Railroad Seminar Series is sponsored by the Norfolk Southern Corporation here at the University of Illinois at Urbana-Champaign. And on behalf of all of us, we want to sincerely thank them for their ongoing support of this seminar series. It's greatly appreciated by us on campus, as well, of course, by the people who are able to participate via the internet. A little bit about our presentation today. Reliable rapid transit operations result from a well-designed service plan. Such a plan must be robust and stable in its particular operational environment. And due to the potential for service disruptions, these plans should incorporate an appropriate level of slack in order to allow the system to efficiently recover to a normal state if these disruptions occur. Insufficient slack may result in unstable service, whereas surplus slack incurs unnecessary expense and waste. Consequently, evaluation of service stability and efficiency is an extremely important topic for metro systems. Dr. Lai and his students and collaborators in Taiwan have developed new approaches and analytical models to help understand and improve this process. These techniques can be applied to help agencies and operators design an optimal metro service so as to provide reliable service to customers while also satisfactory return on shareholder investment. Our speaker today, Yung-Cheng Lai, is an assistant professor in the Department of Civil Engineering at National Taiwan University. He completed his BS degree at National Taiwan University, and then we were extremely fortunate, because I particularly was fortunate because he chose the University of Illinois to pursue his graduate work. He completed his MS and his PhD here, and then returned to National Taiwan University, where he was offered a position on the faculty. Since then, he's developed an impressive body of research and a research program working with his students and collaborators in Taiwan, and has really emerged as I think one of the emerging leaders of rail transportation systems analysis in not only in Taiwan or the United States, but in the world. So we're very pleased to have him back here today to give us a talk on some of the work he's been doing. He's also chairman of the TRB Railway Operating Technologies Committee, and is participating with us also in the New Rail Center, helping us develop and execute our research in railway capacity analysis and various other systems optimization related topics. If you could all join me in welcoming Professor Yung-Cheng Lai. And before we get started, I also want to present Professor Lai with a gift, which he had admired one of these at my home. This is a railroad spike, but it's got some additional features which maybe we can put to use later this afternoon. And then this is the stand that goes with it. So
thank you very much.
Thank you very much for speaking.
Thank you, Dr. Barkin. Before I start, I'd like to say that it's always my pleasure to be back to my second home besides Taiwan. To me, this is where my railway career starts. So it's kind of touching when I go back to my school and sort of like my home. Over the years, over a year, from 2002 to 2008, I was so fortunate to join the program, and then working on the research I love to do, and go to different conferences with my colleagues and presenting our results. So I was so happy, and then I think a lot of you can see a lot of familiar faces on these slides. And then this time I'm coming back not only as visiting scholar over here, but also bring my family, my wife, and my baby boy back to University of Illinois, visiting my beloved school and beloved friends at Urbana-Champaign. So before I start, just like to say thank you, UFI, thank you, Railroad Engineering Program, now the RailTEC, and thank you, Dr. Barkin and our colleagues. All right, this slide just shows a little bit about research interest. Okay, so what I have been working on at National Taiwan University. Over here, when I was a student from 2002 to 2008, I was working on railway capacity analysis. So all my study pretty much relate to this particular topic. When I go back to Taiwan, set up with my research team, and then we have 3 groups inside the team. One working on capacity analysis, so we still look into the service performance and evaluation. And then my second group is working on railway operations and management. So this group is working on service design. So we're looking into how to develop better like stop scheduling, okay, or stopping pattern, or how to devise better timetabling or timetable evaluation tools, and also like a rolling stock scheduling, like and similar topics. So this part is about service design. So that's my second group. And my third group is working on railway safety. So this is another very important topics. We're constantly getting requests from the conventional operator in Taiwan, and then we're working on some analysis and help them. So that's the research groups. Today's topic is about capacity. It's related to the capacity research. So that's why I sort of listed some of the study we have been doing in railway capacity. So give you a little bit overview or background of this kind of research. And to me, I usually separate capacity research in 2 parts. Okay, the first part is capacity evaluation and computation. And this kind of analysis will look into the impact of key capacity factors. So here, maybe like priority of the trains, heterogeneity of the trains. Like this will be like important factor. We're trying to understand the factor, okay, or the impact of this factor. And then based on the important factors, we can develop railway capacity models or trying to understand how to evaluate or monitor the performance of the rail line. So that's a very important task we have been working on and still are working on this kind of topic. And the other category would be capacity management and investment. So this part is actually using capacity model. We're trying to build decision support tools and then using capacity model and trying to help capacity planner to determine what is the best optimal investment plan. So that including strategic capacity planning tools, and also we have this high-speed route improvement optimizer. The second one is trying to combining infrastructure options and rolling stock upgrade together and making the best decision, because sometimes you can reducing travel time by using better rolling stock, just like tilting train, okay, for conventional railway, for the passenger railway. A lot of time you can use tilting train to save your time. And the other way, of course, you can improve the infrastructure, okay, to increase the track class, increase the track speed. So there's some trade-off over there. So this is another topic we have been working on. And the last one listed over here, it's just like, because there's an important impact from heterogeneity in trains. So we're trying to incorporate this particular factor into train network routing, into the optimization of train network routing. Okay, so this is a little bit background and other topics we have been working on for railway capacity. But this one, okay, which is today's topic and also my favorite topic, is after so many years of capacity analysis, we realized there's a relationship between capacity utilization efficiency and stability. And then we're hoping that we can having a kind of methodology and trying to understand what is the relationship. How can we connect these two parts together? And that's the main topic of today. And then the topic is called development of the evaluation process and models for metro system. But actually the same concept can be applied for conventional railway system, or passenger rail, freight rail. It's the same kind of concept. Okay, it's just like the model-wise, the capacity analysis model will be different. Okay, for metro system, you're using different capacity model. For conventional railway, you have another set of capacity analysis. Otherwise, the basic concept will be the same. Okay? The basic concept is the same. Okay? It's just trying to evaluate the efficiency and stability for railway system. So this slide is the most important slide of today. So if you can understand the concept on this slide, and then you're fine. I mean, I don't have much equation today, so this is the most important one, just trying to understand the topic. And then to help you to understand the topic, I call it glass cup theory. Okay, glass cup theory. Usually I put water inside, but because it's a larger room today, so I put juice inside. I may splash in the juice on the ground, but I hope you.
It looked like diesel fuel. I thought
that. Okay. All right. So this is how I call glass cup theory. We're trying to understand the trade-off between efficiency and stability. So for the time being, forget about railway system. Forget about railway. We're trying to evaluate the efficiency of the usage of this cup. Okay, so here you can see there's a size of this cup. Okay, and then there's a juice, the water level. Just using water for now. There's a value you're putting inside the cup. Okay, so you can easily say that this is maybe like 85% of usage, right? It's using 85% of the total volume. That's the efficiency. And efficiency-wise, usually you're trying to maximize the efficiency. Think about this cup on this table. Okay, if I have another cup, okay, has 100% usage, okay, and then these two cups both sitting on this table, very stable, very nice condition. Do they have any difference in stability? I'll say no, because it's a perfect condition. There's no vibration at all. It's just sitting there. So if this is the environment you'd like to using a maximum level of your efficiency, so you try to improve your efficiency, right? So in railway sense, capital investment, right? The infrastructure is so expensive. So you try to maximize your usage of your assets. So you're trying to max out, okay, your system, trying to max out the assets. So that's efficiency. But then let's look at stability. Okay, think about stability. Okay, evaluation the stability of the water level inside the cup is the same as evaluation the stability of the railway system. Okay, no system is perfect. All right, you think about when you're sitting in the restaurant. All right, and the waiter or waitress is just pouring water into the cup. They never fill 100% of the cup. Why? Because whenever you take the cup close to your mouth, there's a vibration of the water level. So you have to build in slabs, right? You don't want this water splashing out. Okay, if you have a little vibration, they can come back to the normal state. Okay, you can recover from normal state. But if you have a lot of vibration, okay, they're spreading out, right? So same thing for the railway system. Let's look at this way. If we relate this to the railway system, okay, the size of the car is just the capacity of the system. Okay, so the capacity will be, for example, we're talking about metro system, will be 10 trains per hour. Okay? For this particular metro system, you can dispatch at most 10 trains per hour. Okay, that's the capacity. That's like the size of the car. And then the usage, the water level, it's just like use capacity. Okay, now according to the service plan, you are dispatching 8 trains per day. Oh, sorry, 8 trains per hour. So using 80%, okay, of your system. So efficiency-wise, it's 80%. Okay, and then the empty space over here, okay, using like 80%. The empty space over here, it's the available capacity. Okay, we can also call it slacks. Those are the slacks built in, okay, to mitigate a possible system failure. So it's really depending on how much is the vibration. Okay, you have to think about how much is the vibration, and then while designing your system efficiency. So you don't want to using too much, and then the system will never recover. But you don't want to using too little because that's a waste of your assets. So the whole idea is just like evaluating the water stability inside glass cup and also the efficiency, okay, of the usage of this cup. So that's the idea. Okay, so here we can say that higher asset utilization may cause lower system stability. Okay, I say may because we're just presenting a perfect condition on the table. Higher utilization may not, right? Because a very perfect condition, the system is 100% reliable, and then you can max it out. Okay, you can max out your efficiency. All right, so may have this kind of lower system stability. But then another point we're trying to make here is like every system should have its own optimum balance between efficiency and stability. Think about a metro system compared to a freight railroad. They have different level of system disruptions. Okay, if you go back to the literature, okay, most of them is European literature on capacity utilization. They usually suggest that 80% is the upper limit of the capacity usage. So using 80%. Okay, all right. But this is like from practical point of view, from experiences. Here we're trying to establish the relationship between them. And then we can say that, oh, maybe for some of the metro system, they're very reliable. You can use in 95%. But for freight rail system or for some kind of system with a lower quality of the track, you can only use in 50%. So there is an optimal balance for every system. Okay. But for this study, what I'm presenting today, I'm showing you the evaluation of the efficiency and stability, and we're still trying to develop methods to find the optimal balance. Okay, because it requires a very distinct or very specific objective function to determine the optimal balance. But that's the goal. How can we actually reach to the optimal balance? That's the goal of this type of research. Okay. All right. So based on that concept, based on the particular concept, then we develop this evaluation framework and models. Okay, just based on the concept I just presented before. And over here, we have 3 modules inside this framework. Okay, let's just start from the bottom. Okay, so the 2 most important attributes to evaluate the operational efficiency and also to evaluate the operational stability. Okay, and efficiency-wise, just as I said before, we can use the percentage of the capacity usage. Okay, and operational stability-wise, we're using a new term, expected recovery time, to evaluate the stability. Later on, I'm going to show you what is this kind of recovery time, what is the expected recovery time. So this is the 2 most important attributes to evaluate this 2. Okay, so we have to build a module to calculate it. Okay, these 2 distinct, these 2 specific attributes. Okay, for this evaluation framework. And then let's look at the top. Okay, let's look at the top over here. These are the model inputs. To evaluate a system efficiency and stability, you need 3 types of inputs. First, you need to understand the system characteristics. And that's a lot of data. You have to understand how the infrastructure setting, how the service plan, okay, how they operate the train. You want to evaluate the capacity of the system. And the second part is a metro service plan, okay, or for passenger railway, could be the schedule, could be the timetable. All right. This part, we're trying to understand what is the use capacity, okay? What is the water level inside the car. Okay, you have this part. And also the third part, you need the historical disturbance data because you need a method to estimate, okay, the possible probability of the system value. Okay, so from the top, we need these three different types of input. Okay, and for this system characteristics, we need a capacity analysis module, okay, to analyzing what is the capacity of system. Just like I said before, how can you determine this 10 trains per hour? Okay, for the other link, maybe 12 trains per hour. So you have to have a method to evaluate what is the capacity of the system. And then not only the normal capacity, you also need to understand the downgraded capacity, which means during the system disruptions, okay, just for example, you have double track and one train blocking one of the track, okay, as a system value. So suddenly you're reducing your capacity from double track to single track. So that's what I meant. This is downgraded capacity. So we have to understand what is the downgrade capacity as well. Okay, so this part should be pretty straightforward. From the metro service plan, we can know the use capacity. So usually metro system, you know the headway of the train, so you can calculate how many trains they're running. And then this part, based on the historical disturbance data, those are just the data, all the data you're collecting. All the data the operator will actually record it regarding like all kinds of system value end up with some kind of delay or some kind of system disruption. So they were recording this type of data. So you can analyze the data and then build two types of distribution. Okay, I'll talk about this in more detail later, but here just give you a heads up. First, you need a reliability distribution for every system value. For every type of system value, you need to develop a reliability distribution. So you need to have a function to estimate the probability. And then this part, maintainability distribution, just used for understanding what is the repair time of the system value. Okay, not only you have to understand, okay, would this system value happen or not? When it happens, you need to have another function to estimate what is the repair time. Okay, what is the repair time to let the system from downgraded capacity back to normal capacity? So that's another distribution you have to establish, okay, over this process. And then when you have all this data, okay, available, you put it into this module, and again, and you can estimate, or you can understand the relationship between efficiency and the stability. All right, am I making sense? Any question at all? Okay. All right. So for the following slide, I'm just giving you a little bit equations. Oh, this didn't show right on the equation, but that's fine. We just show you a little bit information regarding how you calculate, how we actually implement this process and getting the result we're trying to get. So first one, in terms of operational efficiency, this should be very simple and straightforward. We're just trying to understand what is the asset utilization efficiency. So again, based on the capacity model, you can understand what is the normal capacity of the system. Just like I said, the 10 trains per hour will be the normal capacity. And then based on the service plan, you can understand what is use capacity. Just simply take the use capacity divided by the normal capacity. Then you can understand what is you can determine what is the percentage of the capacity usage. So that's simple, straightforward. And usually we just use it like percentage-wise. We can know like how much is your capacity usage. So that's the capacity utilization efficiency. Okay, and this part is new. This part is new. This part is the idea, the attribute we created to understand the stability. And then because we're trying to link efficiency evaluation and stability evaluation together, we're trying to link them together. And we try to link them together, so we need to using the same kind of methodology to evaluate that. So here, we're also using capacity analysis, the concept of capacity analysis, to evaluate what is the stability of the system. Okay, so this is a new application of capacity analysis. So here I have as a demonstration, this figure, the x-axis is time, okay, because the metro system, I separate them into different hours, and the y-axis is the traffic flow. Okay, y-axis is traffic flow. Okay, and I separate them into 5 different time frames. So here you can say maybe it's like around 6 a.m., 7, 8, 9, 10. You have 5 different time frames. Okay, and there's a normal capacity. So for a particular section, okay, you have a long link, and then you separate them into different pieces. Every piece you can calculate its own capacity. So for a particular section, okay, and based on the system characteristics, you can get this normal capacity. And they should be, generally, they'll be the same over time, because that's the maximum limit of your system. That's the size of the cup. Okay, so you can get this size of the cup, okay, as a normal capacity. So again, this can be like 10 trains per day. Oh, sorry, 10 trains per hour. Okay, 10 trains per hour. So that's the normal capacity. Then again, from the service plan, you can understand what is the use capacity, and what is the available capacity, and then you know it for every hour. Okay, so supposing based on how much is your how much time you operate your system, you can generate this kind of diagram. So for T1, T2, T3, T4, T5, they have different usage. You can see that here should be the rush hours, and then you're back to the normal operations. So here you can see that this part, the orange part, okay, is the use capacity, and this is the normal capacity, and this part, okay, will be the slabs. Okay, this is the available capacity. Okay. Now let's look at if something happens. If there's a system value in this time frame, at 7 a.m. Okay, from this 7 to 8, there is a disturbance. There's a system value, and then your capacity reduced from normal capacity to downgraded capacity. Okay, just like I say, it can be from double track to single track, or anything else. Okay, it's based on the type of a system value. Okay, you can determine what is the downgraded capacity. All right. Originally, this is the amount of trains you have to dispatch, right? Let's just say originally you have to dispatch 8 trains per hour for this particular time frame. Okay, but suddenly you can only dispatch like 2 trains per hour. Okay, suddenly you can only dispatch 2 trains per hour. So there are 6 trains. You have to hold it somewhere. Okay, you have to keep it somewhere. All right. And then the next thing you have to determine is like, what is the repair time? How much time it takes? Okay, for the capacity from downgraded capacity back to normal. Okay, that's the repair time. Okay, so for example, the rolling stock, the train blocking the line, okay, for an hour and maybe 40 minutes. Okay, so this is the repair time. Okay, you just move it to somewhere else, or you can repair it in an hour or 40 minutes. Okay, so this is how much time it takes to recover, not fully recover of the system, but recover the system from the downgraded capacity to the normal capacity. And then this black area, you can calculate the area, okay, and then you can get the number of trains to be stopped, okay, or to be halted because of this system disruptions. All right, so these are the trains. You just suppose you should dispatch them according to your service plan, but then because of this system value, you cannot. So you hold it somewhere. All right, and the next step, we make an assumption. After the repair time, okay, the capacity will go back to normal capacity. We're using these rooms to dispatch all these trains. So that's the idea. We're using all these available rooms to dispatch, okay, all these trains to here. Okay. Of course, people arguing that this is not practical. In practical, you're canceling train, you're doing a lot of operational movement. But I have to say that there's always a cost associated with all kinds of decisions. Okay, if you take into account all this possible, like in operation-wise, like canceling trains, okay, you have all kinds of alternatives. You end up with some kind of subjective value. You end up with some kind of subjective judgment. Okay, are you going to cancel the train or not? What is the cost of the train? So here we just keep it simple. We have to dispatch the train anyway. We dispatch them from here to here. Okay, we cannot dispatch from this area. We dispatch by using the available capacity. Okay, at least, if you're comparing 2 different schedules, comparing 2 different service plans, they're on the same page. That's a standard procedure. Okay, at least you can do the comparable analysis by that. So we make assumption over here. Okay, and then based on how much available capacity you have here, okay, you can determine what is the recovery time. And this recovery time is the time the system actually being fully recovered back to the normal state. So after this period, you can see that we go back to the normal operations. Okay, that's the idea. So that's the way we evaluate the consequence of a system failure, and we call it recovery time. Okay, but there's another term right over here, expected. So it should be expected recovery time. Why? Because if we know the probability of the disturbance, then using the probability of the disturbance, probability of the system value times the consequence. Now you have the expected recovery time. Now it becomes an attribute for system stability. Okay, so based on the same idea, we can look at this equation. Okay, so expected recovery time, as I say, just that you're using the probability. If you figure out the probability of a particular system value, and then times the consequence, what is the recovery time of this system value? Okay? For people working on safety analysis, this should ring a bell. This is a risk equation, right? This is a risk, and this is probability times consequence. So I also sometimes call it risk in capacity utilization. Okay, when you are using your capacity, there is a risk associated with it. So we call it risk in capacity analysis. That's how we're calculating the stability. And then for this probability-wise, there are functions you have to develop. So I just keep it simple over here, based on historical data, okay, and then using just conventional reliability engineering method, you can come up with this kind of probability function to estimate the probability of a particular system value. Okay, so here they usually, based on the data you analyze, you can come up with a failure rate. Okay, and then based on what kind of exposure you use, here we're using train hours. Okay, so for example, you're running 10 trains for an hour, that's 10 train hours. Plug in this number, you can find out what is the probability of the system value. Okay, so that's this part. Okay? Just calculating the expected recovery time. And another thing I actually mentioned a little bit, and just to give you a little bit in detail. But we won't get into the equations. Okay, just give you a little bit detail. So another thing we actually mentioned before, okay, when we talk about the framework, is that there's another stochastic property, okay, in repair time. Okay, how much time it takes for system failure, okay, to be for a failure to be repaired or for a failure to be resolved. There's a repair time. Okay, how much time it takes? Okay, or we can say how much time it takes to bring the capacity from downgraded capacity back to normal capacity. That's another part we have to figure out. So that you can also figure it out by using the historic data. Okay, to be simple, you can just use it like mean time to repair. Okay, you're gathering all the data. Okay, how much time they're usually being repaired. You can just use mean time to repair. Okay, so that's an attribute you can use. And over here, we're not only using mean time to repair, we're also trying to understand the range, okay, of this distribution. So we're also using a point estimation method to estimate the range, okay, of this stability. Okay, that's just as much as I want to say on this part. All right. So that's the idea. That's the idea of the whole framework. And I don't want to bother you by the detailed equations. Actually, we have this idea for a long time. We have the framework for a long time, but really gets into the real data, analyzing the result, come up with the result. That's a very painful process, I have to admit, because all the disturbance data are not perfect, okay? And there are a lot of data you have to gather, a lot of data you have to analyze it. That takes a lot of time. But the framework, okay, should be pretty straightforward, all right? So we are actually evaluating the trade-off between stability and efficiency, okay, as I say many times ago. And then we're using three types of data: the metro service plan, the system characteristics, and the system reliability and maintainability. Okay. And then over here, this is just a review. Okay, review of how we calculate that. Okay, how we calculate how we actually get to the operational efficiency and the stability. Okay, just a review. So for operational efficiency, okay, we need use capacity and normal capacity. So what we do is we have a capacity analysis module, takes the system characteristics, and then figuring out normal capacity. And then we have a metro service plan. We can figure out what is the use capacity. And then combining these two inputs into this module, we can get the operational efficiency. Okay, that should be simple and straightforward. And for stability-wise, we need more data. Okay? We need the distribution of the maintainability, distribution of the reliability, the use capacity, downgraded capacity, and normal capacity. So that's why I have to build another module to working on this part. Okay, a reliability module to working on this part. So based on historical data, we can get the reliability distribution and maintainability distribution. Okay, and again, based on the capacity analysis module, we can figure out the downgraded capacity. So from all these five inputs, then what did I do? Okay, yeah, we can put it into this module and finally get the stability. All right, so that's the basic framework of the whole analysis. Okay, and models just within each module. Okay, there will be models for that. All right. So starting from here, I'm going to show you an example and with confidential data. So I can say it's only a metro system in the world. Okay, if I limit it to Taiwan, that's too small. although it's probably from Taiwan. Anyway, we're just conducting a metro system, okay? Conducting this case study for a metro system, okay? And we're collecting all the data from the metro system for a particular line of the metro system. That including the service plane, of course, system characteristics, and historical disturbance data, okay, as I mentioned before. And we're also working on this. We also did the similar study for the Taiwan Railway Administration, which is the operator of the conventional railway in Taiwan. We actually did that before this study. Okay, for the conventional railway, annually they have a schedule change, a big schedule change, a big timetabling change. So every year there's one specific time they change the timetable. So what we do is that we take their data and analyzing the before and after effect. So we analyzing the efficiency and stability for the old timetable, and then analyzing the stability and efficiency for the new timetable, and we tell them what is the impact of the change. Okay, so that's what we did for the past 2 years. We did it twice for their system, and for this metro system, it's a new trial. It's a new trial, and then for metro system, they don't really have an old schedule and new schedule for the time being. So we're just using like weekday service plan and weekend service plan. And there are more trains running for the weekday, and less train running on the weekend. So we're just comparing the difference. For historical data wise, this is for a specific line, okay, for the metro system, a specific particular line for the metro system. And then this one, it's kind of a short period of time. That's the only data we can get. For the conventional railway, we're analyzing like 5-year data. There's like 30,000 excellent data, and then we have to sort of go through out of that and generate the results. But for this one, there are only 200 recorded disturbance, okay, for this 10-month period. Okay, actually, essentially to them, that's still a very, very high number. So based on historical data, then we're analyzing the data. We did cluster analysis, separating into different groups, and then generating the reliability function and maintainability function. Okay, and the system characteristics-wise, I couldn't list out of them. There are just a lot. I just want to say that this this system has like 20+ intermediate stations and 2 terminal stations. So you have to take into account all the infrastructure in order to calculate the capacity. That's again another big task to calculate, gathering the data and calculate the result. Okay. Well, unfortunately, this didn't show right. I was trying to show you the map of the system, which is an adjusting map. I took out some of the stations, so you cannot just plug in the number and figure out what the system is. But anyway, sorry, it's for some reason I think it's an Apple system. Just didn't take my figure. But anyway, this is supposed to be a system map, so you can see all the intermediate station, and there's some crossovers. Okay, there's some pocket tracks, and then there's 2 terminal stations. Okay. Right. So the first thing we did, okay, I'm presenting over here, is the determination of the maintainability. So based on all the disturbance data, all the data on system value, what we did first is we separate them into different groups, okay, and different types. And these types are originally defined by the operator. When they recording the excellent, recording the system value, they'll have the types. Okay, so we just follow them. But for a particular type over here, for example, like train value, okay, we separate them into 2 levels. Okay, we perform cluster analysis and end up analyze the data. We find out that there's 2 different levels inside train value. There's a level that's very little effect. There's another one that's much larger effect, and they come out with different mean time to repair. So essentially, for every group, we're hoping that they're within, like for example, 95%, okay, for confidential CI, 95% CI within this kind of range. So we want to make sure that when we apply the mean time to repair, they are within this range. Okay, so this are all the disturbance. Okay, all the disturbance that we're looking into. Okay, for the particular system. So this are the value we'll be using. Okay, we'll be using for maintainability, for repair time. There's also data over here, the standard deviation. Okay, that's also being used, but I didn't put it over here. For the probability wise, we have to come up with this function.
Correct.
Yes, please.
The previous slide with minutes or hours or something else. Mean time to repair.
I think it's minutes. Yeah, I think it's minutes over here. Correct. Yeah. Sorry, I didn't have the unit over here. Yeah. Okay. All right. Then over here is the probability of the system value. Okay, so here we have to come up with this function to estimate the probability of the system value. And these are the results. So again, we're following the same cluster analysis and then come up with a value rate for every one of them. Okay, so when you have a lambda, you just simply plug in the exposure, okay, and then you can come up with a probability of a particular system value, the probability of the particular system value. So that's the probability of the system value. And let's look at the overall evaluation results. Okay, essentially for the analysis, we actually break them for the whole system. We break them into we break them into sections. There are a lot of sections, and then we break them into every hours. Okay, so I'll show you later on over here. Maybe just jump to later. Yeah, so that's the detailed analysis. It's a 3D diagram. Okay, and this part representing all the sections. This part representing the time. The y-axis is the efficiency. Okay, and then every bar actually representing for a particular hour or particular section what is the efficiency or expected recovery time. So that's what we do. But this table is an overall evaluation result. Okay, what you can see over here is for the row. This row is representing the operational efficiency. Okay, and this part is a weekday service plan, and this part is a weekend service plan. And there are two directions of running, so we can calculate for one direction, like westbound direction, okay, will be this, and eastbound direction will be this. All right, let's just look at the overall results. If the overall result wise, in terms of operational efficiency, okay, the weekday service plan, of course, using the asset more than the weekend service plan. So increased from 21% to like 30%, okay, 31%. So increased by 46%. And then if you look at the stability, okay, it's actually from 0.438 to 1.356. So this range, okay, is about plus about 200%. So what I want to show you over here is like they are actually they are actually moving in the same direction. Okay, when you're increasing the capacity utilization level, you are increasing the instability. Okay, instability, but they're not increasing the same amount of same rate. Okay, they're increasing in a different rate. So that's why you need to have a method to establish this relationship, understanding what is the relationship between efficiency and stability. All right, so this is just from overall results. And then we can look at more detailed results. Okay, I'm sorry, I have to squeeze all the data into this slide so you could even see the axis. All right, so again, this part is all the sections. Okay, or you can easily just think about all the stations in the metro system. Okay, but actually when we calculate a section means between two stations, we have to calculate in the departure headway, the arrival headway, and also the line capacity on the particular link, and then just determine the capacity that way. Okay, we took the minimum value as a capacity. But anyway, so this is a location-wise, all the section, what is the capacity, and this is time-wise, and then Z will be the efficiency. So for weekend, wise, okay, they're generally okay. You can they're generally like in low efficiency usage. Relatively high operational efficiency happen at the terminal sections and section near the station BR4. So this is the terminal station, and this is also a terminal station. And this is one of the big stations in the metro system. Big station means a lot of passenger, okay, on board, a lot of passenger boarding or alight from there. So that's a station with a little capacity constraint. So this is one of the results you can see. So that's efficiency, okay, and for two different directions. So again, this is for westbound, and this is for eastbound. And let's look at stability, okay. It's all blue. I'm sorry. Later on, when you see the weekday data, it's much more colorful, okay. So this just shows you that stability-wise, they're not having much problem because there's very low usage of the system, okay. But at this, if you look closely, you can still see the variation. So relatively high expected recovery times observed at the terminal section, okay, in the section near station BR4. So again, when you increase the efficiency, you are increasing the instability. Okay, you're increasing the expected recovery time. So that's for the weekend. Okay, let's look at the weekday data. Okay, weekday data. So again, this is the sections. This part is time, and the y-axis, the z-axis, it's efficiency. So here you can see clearly, okay, the effect on terminal, okay, and on the terminal section and the section near the station BR4. So again, same thing happened over here, but in more significant scale. All right, And stability-wise, okay, they have similar results or similar effect, okay. And then you can clearly identify, okay, there's a peak hour effect. Okay, look at here. This is like a time-wise. So there's a morning peak hours and there's an afternoon peak hours. So because of the peak hour usage, you can also have higher stability at that time. So this method helps you pinpoint the problem. Okay, what is the section and what is the time? Where are you having this kind of high instability? So this analysis just instead of using the overall analysis, overall result, this actually helps you to pinpoint where the problem is. Okay. So another way to look at the result is to using this 2D diagram. Okay, using a 2D diagram. And then here, the x-axis now is all the sections. Okay, and the y-axis, okay, on the left is the expected recovery time. Y-axis on the right is the efficiency. Okay, so here we're not talking about time effect, which should average out the time effect. So here we're looking at sections. All right, the orange layer shows you operational efficiency, and the blue line shows you the stability, expected recovery time. You can see that they're having sort of the same trend. The highest level is actually happened near VR4, again, near this large station. So that's where you have high capacity usage and very high instability. Okay, and you can see the dash line over here, and the dash line along the blue line. The dash line is where I'm talking about that there's uncertainty in maintainability. So because of that, you can create this kind of range, okay, along this blue line. And you can see that over here, it's also intuitive. Over here, when you have a large instability, this range is also larger. Okay, so this is the one of the result you can see. And then this is another perspective in time. Okay, so now x-axis is the time. Okay, we're not talking about location-wise. We're averaging out the effect of location-wise. And then clearly, you can see that. Okay, there's a morning peak and there's an afternoon peak. Okay, so that's again just another way to look at the problem. Another way to look at your system efficiency and stability. And again, you can see that there's a very close relationship between efficiency and stability. All right. So the last thing I want to show you. Oh, please.
We'll just wait.
Okay. The last thing I want to show you is another way to use this kind of analysis. Okay. What I have presented you before is pinpoint the problem. Okay. Figuring out where are the problems. Okay. Now, if you pinpoint, if you find out the problem, okay, or you found the instability, the stability is not acceptable, what can you do? Okay. If this system, the stability of the system now is not acceptable, what can you do? So here, just shows you some of the methods you can do. One, you can adjust your service plan. Of course, adjust your service plan running less train, reducing the operational efficiency. You can increase the stability. Second, you can improve capacity. That's the same thing. If you, in terms of reducing the usage, reducing the efficiency level, okay? Because you increase the normal capacity, okay? You keep the same service plan, okay? Because you have to run those trains to meet your demand. You increase the capacity that way, okay? Another way to improve your system would be improve the system stability and maintainability. That means that for some system, for example, for the system I showed you just before, okay, there are a lot of system failure on communication system, a lot of system failure from communication system. So what they do is that they actually upgraded their communication system. Okay, but before you're making the decision, this tool can help you to evaluate what if you upgrade your system. What if you're upgrading your system reliability? What can you see? What's the impact from that? So that's something we can show you. We can help you on that. So this is pretty much the last slide with the results. Okay, and this slide can show you, some of the adjustment you can evaluate. For some of the adjustments, some of the improvement, you can evaluate the results over here. So again, I'm sorry, figure didn't show on my computer. The x-axis over here is the daily operational efficiency. Okay, so 0.3 is 30% usage, and the y-axis over here, the daily expected recovery time. Okay, and then for your system, okay, we can using the proposed method to develop this line. So this is a relationship. When you increase your operational efficiency, this is what you're going to see. That's the expected recovery time. So this is the original system. So For example, right now they're using, overall wise, they're using like 31% of the efficiency for the whole day. And of course, the peak hours, but for the whole day, it's only 31%. And then you can find out that they're subjected to 1.356. Okay, this 1.36, this kind of stability. Okay, and if this is not acceptable, just as I said before, okay, you can upgrade your system. So for this particular example, we actually mimic what they do. We actually take the result. Okay, when they upgraded their communication system, okay, you're eliminating, pretty much eliminating the type of values. Okay, and then the blue line is representing the new status, the new systems, okay, the new relationship. So for the same kind of usage, still 31%, you are reducing your stability, or you're reducing your instability by 20%. So you increase your system performance by upgrading the communication system. So again, this method, okay, we build up this kind of relationship, can help to understand for different ways, for different methods. Just like here, if we go back to this kind of scenario, okay, when we talk about adjust service plan, that means you're moving from this direction. You can just adjust your service plan by reducing your operational efficiency to this amount, and then you can get a lower daily expected recovery time. So along this line, you're talking about the impact from adjusting your service plan, and then if you have any upgrading to the system, you're creating a new line to understand their relationship. Okay. So in conclusion, with the proposed method, okay, the metro operator can examine and monitor the stability and efficiency of their proposed or their operational plan. And we found that usually operational instability usually increases with the operational efficiency. Okay, so the proposed method can help users establish and understanding this kind of relationship, and also it can help justify whether the improvement strategy will be cost effective or not. Okay, that's the conclusion of this study. And for future work-wise, okay, we're proposing that every metro operator or every railway operator actually should closely examine the disturbance data. Okay, they should keep a database on all these system disruptions. Okay, because system will change over the time. Okay, system will change over time. So what we're proposing here is actually you can set up a time frame. Okay, for example, you're always looking back 3 years. Okay, looking at how the historic data for the past 3 years, and you'll keep moving. Okay, for this year, you're looking at the previous 3 years. For next year, you're looking for previous 3 years. You're moving at this direction, so you can updating your system status because your system status is changing over the time. Okay, and this status will actually telling you this vibration. What is the amount of the vibration? You have to capture and monitor this amount of vibration in order to set the right service plan. Okay, so you want to know the most up-to-date system reliability status. And the second one is we're still working on this. We're still focusing on the determination of the optimum balance. Okay, what we have been presenting is 2 attributes: efficiency and stability. But because the attribute we use for stability, which is expected recovery time, that's a new attribute. So for railway operator, they just couldn't say that what is the acceptable level. Okay, we have to do more analysis to understand what is the impact of this expected recovery time. Okay, and then we can creating a kind of objective function. Okay, for this trade-off, and then end up with an optimal balance. Okay, one thing we can do perhaps is that think about if you don't using expected recovery time, you can simply using delay, right? For different system value, there's an associated delay, right? So for different capacity usage, there's associated delay. And if using delay and efficiency, you can create some kind of optimum balance. Okay, just give you an example. As a user of the metro system, okay, you like the system headway to be shorter possible, right? So you don't wait for a long time. So usually what we calculate, like if the headway of the train will be 5 minutes, and then the typical waiting time is half of that. So waiting for the next metro train will be half of that, so 2.5. All right. And you can creating this kind of optimum balance by using what is the minimum time for a user using the system from their origin to destination. Okay, think about that. when you're increasing the efficiency, you are reducing the headway. So people can get on train as fast as possible for the ideal condition. But then there's a condition that when you're reducing the headway to a sense that the system is not unstable anyway, okay, they're creating a lot of system failure. Now you get on train faster, but then you sit in the traffic because there's some kind of system failure. End up with or end up with a longer travel time. So that shows you the trade-off. So minimizing your travel time can be one of the possible objectives to find the optimum balance. Okay, I hope I'm making sense over here. Okay, so if you're reducing headway, sometimes you're increasing your system instability, end up with longer travel time. So there's a trade-off. That's a trade-off you can establish right now. Okay, but just like over here, we're not using delay for this analysis, so we're still trying to understand the attributes. Okay, so finally, I'd like to thank you again for coming to this seminar, and I'll be happy to answer any of your questions. Thank you. Oh, please.
Just had a couple. You got to this with your last comment, but with regard to operational efficiency, are you, in this study, are you essentially just looking at trackage utilization, or does your efficiency formula essentially also penalize idle rolling stock and empty seats and things like that?
Oh no, only the track utilization.
Okay,
so you transfer it out. Yeah.
Because I was a little bit confused on your graph that showed the impact of failures across the whole system. It was surprising that in a metro system we have that much variation in efficiency from one end of the system to the other. Because one would expect, a train enters the system, one end goes to the other end, turns around and comes back. So you think that a failure anywhere along the line would have a more drastic impact.
You're right. Actually, efficiency-wise, for the same time frame, they're actually setting the same kind of error. But the difference is the normal capacity will be different. For every section, we calculate their own capacity. So, like for this,
I see. Okay. So
yeah. So, but for this station, they have a long dwell time.
Okay.
So they're actually using up the capacity. So it's essentially the same service plan with the same headway, but then you end up with different efficiency.
Okay, so it's dwell time essentially at the station that's the primary driver of that.
Exactly.
Okay,
Yes.
my other comment was that was on the efficiency side. My other comment was on the stability side. It seems like you hit on something really important, which I've never really thought about, which is that in most of the capacity studies we see that are done for freight rail, the metric that they use for the cost function essentially is typically the sum of the excess costs incurred over the entire event until they get back to normal, right? So extra fuel, extra rolling stock utilization, that type of stuff. But it strikes me as in the passenger model, I think the idea of using expected recovery time is great because the contract with the customer is fundamentally different. Right? Freight, you don't really care how long it takes to recover within reason. The coal can sit there for a day on the side, and as long as when you get 2 coal trains there tomorrow instead of one today and one tomorrow, the customer is really care, the coal is really care.
Actually, I take huge exception to what you're saying, but the premise is okay. Though.
Okay. In passenger traffic, though, you've got the single biggest driver of perceived quality of service is typically on-time performance,
Right.
or headway.
Right.
And so I really like the idea of using a metric that is closer to the actual cost incurred. I'm thinking about all the factors that can go into that, right? You hit on that again sort of in your last comment about you need to look at in terms of recovery time. If the airlines, for example, when a flight's late,
Right.
they just cancel the flight, so their other flights can get there on time, right? You have the option to, if you wait long, if people get disgusted enough, they'll walk away, and that sort of helps you recover, later. So I think the metrics and the mechanism by which you recover seem fundamentally different in the freight universe and in the passenger universe. So I think it makes a lot of sense to use it. How long to get back to normal when people then recover their confidence in the system and come there and trains there. I think that's a great idea.
Thank you to bring this up. Actually, one thing I didn't show you here is like there's a reason why we didn't use delay as a first trial. We're using expected recovery time. It's actually delay is a loosely defined term. For passenger railway, some of passenger railway that look delayed for the very last station. Trains can be delayed in the middle, catch up later. Okay, you didn't capture those kind of results. You're just calculating the end result. Okay, so to me that's sort of like underestimating, because over here you actually create some kind of disturbance. Okay, you're delaying in the middle of the network, but at the end you somehow catch up and there's no delay. And another way to calculate delay will be counting every station by every station. So supposing you have the train delayed for 5 minutes, at the end it's delayed 5 minutes, and then it's like, if you go over 5 stations, it's becoming 25 minutes. Okay, 5, 5, 5, add up together. To me, that's overestimate. So because delay is sort of a loosely defined term, so when we develop this model, it's like we think that we should be using some kind of more standard way or a standard process to compare to do this comparable analysis. That's why we try to develop this new effective recovery time.
You really want the metric of customer satisfaction, right?
Right. That's right.
And that's a much more difficult number.
Yeah. Thank you. Okay. Please.
In your model, you're looking at service disruptions, but you can just as well include planned work. It's considered service disruption in your model. So if I knew that I had to renew the rail over the line, I would say, okay, I'm going to need this section out for so many hours, this section so many hours. And even though it's not something that growth would be considered service disruption.
For sure. I mean, if we have the data, you're just reducing the capacity from normal to downgrade, and then you know the time. So we probably don't need to estimate. Okay? If you know exactly what is the time window, and then we can use the same kind of analysis and then perform that to understand the stability.
Related to that, when you look at it as a section that's either open for traffic or closed, or you have in between. Say I had normally a 60-mile-an-hour track that I have down to 40. So it's affecting the capacity even when it's still
Well, that's part of the capacity margin, though. Yeah, that's part of the capacity margin. If you lowering, well, there's some of the system value is actually just like that. You have a train value, but the train can still run at certain speed. So essentially, that's similar to that. And then you have to account for what is the capacity of that level. So that's why over here for this analysis, we refine the capacity analysis model. Before, we usually calculate capacity for the perfect sense, right? The ideal condition, putting all the input data, okay, operating characteristics, traffic characteristics, and infrastructure characteristics to come up with the maximum value. But here now, there's system value. So we have to understand what is the impact of the system value, what are factors go into the system value, and then what is the capacity of that kind of condition. So yes, if we can define well of a particular condition, then we can model it over here. It's for this part, based on the capacity model.
And then one last clarification on expected recovery time. That's not just the time to repair whatever it was that was delayed, but then it's for the system to get back to it includes the time to repair.
That's one thing. Our team members in the group are still arguing. I can go back to the slide. That's a perfect catch. Okay. So I think what Conrad is saying that we should be counting the recovery time from here to here, because that's real the system recovered, okay, from the beginning to the end. For the conventional railway system, that's what we did. For the metro system, I have the student working on this arguing with me. He's saying that you're double counting because the impact, the impact from here, okay, the length in this direction will actually affect the impact over here. So he just said that that's double counting. If you count it over here and you count it here again, that's twice. So I accept his argument. So that's why in this analysis, we keep it this way. So we're separating the repair time. We're separating the recovery time from the repair time. So they're not part of recovery time. But I think that's something we can go a little bit more detail, go a little bit more deep to try to understand what is the attribute and what is the right value to use.
But I like the expected recovery time better than delays because in my experience, we would be measured against if the piece of infrastructure failed, how many delays would this have?
Right.
But that's highly dependent on where you are in the network and at what time it's a failure.
Right.
So,
and this this can go even deeper. It's very interesting. The delay is also related to how much is your available capacity. If you have a very low capacity usage, and then it's fine. I mean, even you have a system failure over here, then you have a lot of space over here. Okay, what we found for the passenger rail, for the conventional rail, they have the highest instability during the time, even in peak hour. Because for even in peak hour, it's always like 90%, 90%, 90%, 90% for 4 hours. And then you just don't have room to mitigate any system disruption. So what we suggest then that's maybe you can think of like, this kind of zigzag, okay, having a high one and give a little bit room for the second time frame. Okay, so having those kind of room can help your stability. Yes, please.
Conrad's question and observation combined with your presentation and response causes me to think of something that it occurs to me that at different points on a route, let's just say a route, and you've got points where you have more or less excess capacity or sort of more or less ability to recover. That maybe a train gets delayed 5 minutes. I'm thinking more, not so much metro, but northeast quarters. And it's not very significant. You come into the station 5 minutes late, but that's the extent. But at some point, and I'm thinking of the Hudson River tunnels, a 5-minute late train is going to wreak potential havoc right there, whereas it doesn't have much consequence in other parts. So the point is,
Well, we had if it's in the middle of the rush.
oh, right.
In the middle of the night.
In other words, yeah, right. So but the point is, the points where you're most capacity constrained, probably is a sort of a generalization of where you're going to have the greatest problem with these
Exactly.
delays. So this sort of raises, maybe to me, interesting questions about, where you can have tolerance for delay and where you can have intolerance. So, if you're 100 miles south of this place and you're 5 minutes late, well, you want to get back on time by the time you get there, and that becomes a much more urgent problem if you're only 20 minutes. Actually, if you're only 20 miles early, it's too late. But the point is, there's sort of this combination of location and temporal impacts of train delays on the stability of your system.
I'm just showing you that. Yes, and we can develop that. Let me just jump out. For the curve I just developing, I'm showing you over here. Oh, I have to present it. Excuse me. We can have this for every section. So for every piece of, for every subdivision or every piece of railroad, you can have this curve, and then you can understand the impact, okay, from the efficiency and the stability, and they'll be different. Here I'm just showing you the consolidated result for the total system, but of course, it's the same idea. You don't have to add them up. You just perform like essentially we're actually doing like specifically for every section, okay, and every time frame. And then here you just can plug this effect, and then you can try to understand where is the place you may have more slacks, you need more slacks, and where are the places you need less slacks. Yeah, but that's a good point. I have not.
The point is there's a disutility function associated with delays that varies depending upon where you are, and the impact of that delay may manifest itself very far away from where you are at the present time. So the point is you have another sort of tool, which is you have the more distance you have, the time you have between where you are now and your delay and where it's going to matter is another approach to how you manage the recovery.
Yeah, thank you. Please. Yes.
Should I, for every additional rolling stock, bus, what's the probability of service interruption? Can I have that running right on the side of the depreciation? Then you have to also think about new drivers, wage rate, overtime, or what have you. So, and a lot of them, we get subsidized from the government. So much of the grants probably don't even put into that scope, budgeted for
Mhm.
additional capacity.
Right.
So what do you say of those type of agencies?
I'll just say that for those kind of circumstances, you cannot easily improve your system, but you have to understand, you have to understand the relationship. Okay, you have to understand the relationship so you can apply this methodology and understand for your system, okay, what is the stability for now, and what is the stability. You can still analyze stability, and then for those kind of system with less quality track, more system value, maybe you need to use invest. Okay, but of course there are other constraints. There is some service commitment you have to meet, so that's just a fact you have to accept. But at least you can know that where is optimal balance and where is you are right now. So for long-term plan wise, you may want to try to get to your optimal balance. And that's what I was saying for those kind of circumstances. Please.
During your discussion with Professor Barker made me realize what you have here also is potentially an excellent model for predicting the impact of making a case for congestion pricing. You demonstrated right that you have the most risk in these peak periods, so you can now essentially quantify the extent to which it's worth it to incentivize people to travel without peak times.
Sure. Thank you. I'll jot that down. All this discussion actually helps myself and helps our research direction as well. Yeah. Any other questions?
Can we go back to slide 23 again?
Okay.
I'm sorry. I thought it was 21 before this.
Mhm.
Yeah. So I didn't understand in this one why the operational efficiency curve in these sort of outside the peak areas
Mhm.
is kind of just flat, whereas your expected recovery time kind of fluctuates. It seems to me they were sort of
Yeah,
correlated.
they should be correlated, but for this metro system, it's kind of special. They have different downgraded capacity for each section. The reason being that for a metro system, they usually don't have a lot of they don't have crossover for every station. So whenever something happens, station near the crossover will have higher capacity compared to station away from this crossover. So the downgraded capacity are different. So then that's why you can see this kind of variation, even though they're sort of in the same service level. Yeah. So that's actually gets into the capacity analysis. You have to understand where is the siding, where is the crossover, and then what is the downgrade capacity. So. Right. Okay. If not, thank you very much. Thank you.
So my E4 section, of course, we've got to run
Okay.
last 2 minutes. I'll be there.
Thank you.
If other people want to stick around and talk to us, I'm saying some more.
Thank you.
All right.
Hey.
What you do is you come back to
Probably that you probably want to.
Yeah.
where we connect.